Today, we're going to pull back the curtain on the magic that happens inside every single device you use. We're going to get right down to the core of what computation even is by looking at one of the most brilliant and simple ideas in all of human history, Alan Turing's universal machine. So, where are we headed? Well, here's the game plan. First, we'll ask what an algorithm really is. Then, we'll meet Turing's incredibly simple machine, see it actually do something, and figure out how you can build bigger things from these simple parts. And finally, we'll run right into the wall, the absolute limits of what computing can ever do. All right, first things first. Before we can even get into computers, we have to talk about the main ingredient, the secret sauce that makes them all work, the algorithm. I mean, you hear this word everywhere, right? The algorithm for your social media feed, algorithms for trading stocks. But what is it? What makes a bunch of steps an actual algorithm? You know, we have some pretty good everyday definitions. It's like a recipe for getting an answer, or a finite list of instructions. My favorite, though, is the last one. I don't know what it is, but I know the difference between an algorithm and a cow. And that's funny because it's so true. We have this gut feeling for what one is. But, you know, to build the entire field of computer science, a gut feeling just isn't going to cut it. We need something solid, something precise. And that need for a rock-solid definition, well, that's what brings us to a pivotal moment in history, all thanks to the mind of Alan Turing. See, back in the 1930s, Turing wasn't trying to build the next laptop. He was obsessed with a much, much bigger question. What can we actually solve with a step-by-step process? What are the absolute limits of mechanical problem solving? He had to define what computation is. And this was his answer. It wasn't a physical machine with gears and electricity. Nope, it was an idea, a thought experiment. Just imagine this. You have a tape, like an old film reel, that's infinitely long, and you've got a little head that can look at one square on that tape. All it can do is read what's on the square, write something new, or move one step left or right. That's it. Seriously, that is the entire machine. It's so simple, it's almost funny, but it changed the world. The machine's brain is just a simple little rulebook. At every single step, it just does this three-part dance. 1, read the symbol under the head. 2, check your rulebook to see what to do next based on your current state and that symbol. 3, do it. Either write something new, move left, or move right. That's the whole loop, happening one simple step at a time. Okay, this is where it all stops being abstract and gets real. Talking about it is one thing, but actually watching this little machine think, that's where the magic is. So let's run a really simple program, step by step. Okay, here's our mission, and it's super simple. The machine is sitting on a tape that has some A's and B's written on it. Its entire job is to just keep moving to the right until it finds the first empty spot, and when it does, it writes the letter A there and then just stops. That's it. Let's walk through this. Look at the top row. The machine is in its start state, iota, and it's reading a B. The rule is simple. If you're an iota and you see a B, just stay an iota and move one step to the right. So boom. Look at the second row. It did exactly that. Now it sees another B. Same rule applies. Move right. Okay, now look at the third row. It's finally hit a blank spot, that little delta symbol. Now the rule for this is different. It says, write an A and go to the halt state. And that's exactly what it does in the last row. It writes the A and stops. Mission accomplished. It worked. But what happens if the rules aren't so well designed? You can actually write rules that trap the machine. It might just end up shuffling back and forth between two squares forever, never reaching that halt state. And that's a huge idea. Not every program is guaranteed to actually finish. Some just run forever. So finding a blank space is a neat trick, but that's like having one single Lego brick. The real power, the amazing part, comes when you realize you can start snapping these simple little machines together to build something much, much bigger. So, let's create a little toolkit of basic machines. We can have one called R that does nothing but move right, an L that only moves left. We can have a machine that just writes the letter X. We can even have slightly fancier ones, like a machine that moves right over all the blank spaces until it finds the first letter. And now we can wire them together. You can basically make a flowchart. Start with this machine. When it's done, look at the tape. If you see an A, then run this other machine. But if you see a B, run a totally different one. All of a sudden, just by combining these tiny, simple Lego bricks, you can build programs with real logic, programs that can do incredibly complex things. And this ability to build anything, well, it leads us to the most powerful and, honestly, mind-bending part of Turing's whole idea. Because this simple machine doesn't just show us what computers can do, it shows us what they will never be able to do. This right here, this is the big one. It's called the Church-Turing thesis. It's not something you can prove like a math theorem. It's more like a fundamental law of the universe. And what it says is that any problem that can be solved with an algorithm on any computer we've ever built or ever will build can also be solved by one of these simple little Turing machines. It's the universal model, which means if a Turing machine can't solve a problem, then nothing can. It's fundamentally unsolvable. This power means we have to be really careful about what solving a problem even means. Think of it like a detective. For some problems, the Turing acceptable ones, the detective can find the evidence to prove the answer is yes. But if the answer is no, the detective might just keep looking for clues forever and never be able to close the case. Then you have the Turing decidable problems. For these, our detective is a superstar. They are guaranteed to give you a final answer, every single time, yes or no. The case always gets closed. And here's the kicker. There are real, important problems out there that are fundamentally undecidable. The most famous one is called the halting problem. Basically, can you write one program that can look at any other program in the universe and tell you for sure if it will eventually stop or if it will get stuck in an infinite loop? Turing proved it's impossible. No algorithm can ever exist that can solve that for all cases. This pyramid basically gives us a map of the entire universe of problems. Not all problems are created equal. Down at the bottom, you have the simplest stuff. As you climb up, you get to the decidable problems, the ones computers are great at. Go higher, and you find those acceptable problems, where you can prove a yes but a no might take forever. And way up at the very top, that's the realm of the impossible, the problems that are fundamentally beyond the reach of any computer ever. In the end, what Alan Turing gave us with this simple idea of a tape and a head was so much more than a blueprint for a computer. He gave us a measuring stick for logic itself. He drew a line in the sand between what is knowable and what might be forever unknowable. And he left us with a pretty deep question to chew on. If this simple mechanical process can model any computation, what does that say about the limits of our own thinking?